Hello everyone. In the last session, we looked into the shape functions of beam element in terms of Cartesian coordinates, which are in the form of x, and in the form of natural coordinates, which is the xi or s. And also we looked into the derivation of the shape functions for the nodes in a 2D element, such as the rectangular one here, and we obtained the shape functions using the standard procedure of assuming a shape function and then using the boundary conditions or the constraints at each nodes for the shape functions to obtain 4 equations and solving them uniquely using the matrices. Now today we are going to look further into the shape functions, look into detail on the shape functions and understand how we can obtain the shape functions geometrically or just by looking at them. Let's understand more about the shape functions. Let's say we have a 2D element like this, and its deformed shape under certain loading may be something like this, and we want to approximate this exact solution by using the shape functions. Generally, what you can do is, let's take the triangular element. If we mesh this element into very small 2D elements like this, such that when we numerically solve this, then we can get a solution something like this, which may be close to the exact solution. This is one way of doing it. Here what we have done is we have used very finer mesh here, very tiny elements rather than a continuous element to approximate its solution. It is kind of like refining your meshes. The other method is, if you have a triangle like this, the same triangle, what you can do is, if these are the nodes at the ends, we can increase the degree of shape functions such that our solution is quickly converged. If I show this in the isometric form, it may look something like this. As we know that each node will have its shape functions. Now here, as per the definition of your shape function, your shape function, if you are looking at node 1, then its value must be 1 at n1 and 0 at all the other nodes. Now when you plot this, what you get is you get a linear line. This is similar to what you looked in the bar element. So in the bar element, what you had was you had a displacement here and a displacement here, isn't it? Or in bar element, what you had was you had a degree of freedom here for node 1 and node 2, and when you obtain the shape functions for n1, it looks something like that's 1, that's 0. And if you look at the shape function for n2, then n2 will be something like this. So this is linear. If you look at the same triangle in the isometric view like this. Now if we increase the degree of the polynomial, that means we want to change this to a quadratic or cubic or of higher orders polynomials. When you do this, your rate of convergence is quick. To do this, we can add certain nodes. We can add a node here, we can add another node here, and another node here. Now we can name this as 4, 5, and 6. When you plot the shape function for n1 using the definition of the shape function for n1, at 1 your value should be 1, but at all the other nodes your value should be 0. When you plot it, your shape function may look something like this. See, it is 0 here, it is 0 here. Similarly, in this direction as well, it is 0 here, it is 0 here. Now since it is 0 and 0 here, it is automatically 0 at 5. So you see that except node 1, where its value is 1, all the other nodes have the value 0. Similarly, let's say for n4, this is n4, so it will be 1 here, and at all the other nodes it must be 0, so it will look something like this. And here also it will be like this, so it is 0 at all the other nodes. And similarly, so this one you see is a quadratic curve. It is not linear anymore. And what you can do is we can also increase the number of nodes. So this is a 11 noded triangular element. So for this case also, if you plot for n1, you will have 1 here, and at all the other nodes your value should be 0. So it is 0 here, 0 here, 0 here, and in this direction as well. So it will be 0 here, 0 here, and 0 here, and 0 here, and 0 here. So your shape function would look something like this. Now this is the definition of the shape functions, and as you can see that higher the number of nodes, the higher the degree of shape function. Now let's go back and look at our Pascal's triangle. So your Pascal's triangle for xi and eta natural coordinates, we will have 1 here, xi, xi square, xi cube, eta, eta square, eta cube. Here you'll have xi eta, here xi square eta, here xi eta square, and then you can have xi 4, eta 4, and then this will be xi cube eta, xi square eta square, xi eta square. So this is the form of the Pascal's triangle. Now here you can see that this portion here is linear as it has degree. Let's see, this is p as 1. This one is quadratic. It has a degree of 2. This is cubic. This has a degree of 3, and so on. As we have seen earlier, that this Pascal's triangle provides a method of assuming the shape functions in different degrees of polynomial. For example, if we take an order of p equals to 2, then what you have to do is we look at p equals to 2, which is this one, and then we have to take all the terms above and in the line of the quadratic. Now your equation n xi in a 2D form will be a0 plus a1 xi plus a2 eta plus a3 xi square plus a4 xi eta plus a5 eta square. Now you see there will be 6 number of terms. Now the number of terms from the Pascal's triangle to make the shape functions complete will be given by p plus 1 p plus 2 by 2. So now this will be your number of terms. If p equals to 2, then you can see that it will be 3 into 4 by 2, it gives 6. Now there will be 6 number of terms to make these shape functions complete. Now please remember not to forget any of these terms or these monomials while solving for your shape functions. Let's say if you miss one of the terms, let's say this one, then it may affect your rate of convergence. This is a function of xi and eta. We learned a method of solving this. Let's say for a triangle like this with 6 nodes, this equation is complete. You can form a grid with xi and eta, and then you can obtain your coordinates here, and then you can substitute your natural coordinates into above equation, which is this one, and then obtain 6 equations and then solve them uniquely, like we did for the 4-noded rectangular element, like this one here. Here we assumed a shape function having 4 terms, 4 coefficients, and then we used 4 constraints to obtain 4 equations, and then we solve for our coefficients. Rather than going through that procedure, what we're going to do now is we're going to solve by just looking at them. Now for the first case, we'll solve for a 4-noded rectangular 2D element, like we did the last time, but here we'll be doing it slightly differently. Now if we assume our natural coordinates having origin at this point, which is 0, 0, and then this is the xi coordinate, this is the eta coordinate, and you see that this length here will be 1, this length here will also be 1, even in this direction. This length will be 1 and this length will be 1. So this element here is known as the master element, with sides 2. Now define our shape functions in the master element. If we write our coordinates based on this, let's try to find our shape function for 1, that is n1. I'll draw this in isometric form. Now by definition of the shape function, what you'll have is for n1 at 1, its value should be 1, isn't it? and then your value here at 2, 3 and 4 must be 0. This is your xi direction, and this is our eta direction. You see here that along this line and this line, your safe function n1 is 0. So what you have to do is we have to find the equations of the lines which join 4 to 3 and 3 to 2. Now for the 4 to 3 one, which is this and this, you see that its equation is eta equals to 1. So you write here eta equals to 1. Our eta equals to 1 consists of nodes 4 and 3. Now we're left with 2, isn't it? We're looking at this point. So you see that along line 2, 3, which is this one, the value of your shape function must be 0, and the equation for this line is xi equals to 1. This is the equation containing your node 2 and 3, and this one is the equation containing your nodes 3 and 4. Now we have to form an equation that contains these two equations here. So that equation will be in the form xi. This equation is xi minus 1, that is 0, this one, and eta minus 1, that is this one, with some constant c1. Now this constant is here because we have one more condition to satisfy, which is this one here. So at node 1, the value of n1 equals to 1. Now if you do this, 1 will be equal to c1. Now your xi and eta for 1 is minus 1 and minus 1. So what you do here is you write minus 1, and then minus 1, minus 1, and minus 1. So what do you get? c1 will be 1 by 4. And then you can substitute this value back here. Then what you get is you get your n1 equals to 1 by 4 xi minus 1 eta minus 1. If you look at n2, now if you look at n2, which is this one, now your shape function at 2 is 1. The value of a shape function at node 2 is 1, and then at other points it is 0 and 0. We are looking in direction xi and direction eta only. Now for this case also, you see that the value of the shape function, this is n2, n2 is 0 at 1, 3 and 4. Now you have to form the equation which joins 3 and 4, this one and this one. Now this is given by eta equals to 1 and 1 and 4, which is this one here. The equation for this line is xi equals to minus 1, and therefore we have equation that is xi equals to minus 1. This line here consists of points 3 and 4, and this line here consists of points 1 and 4. Therefore we have included all the points 1, 3 and 4. Now our equation n2 will be equal to c2. Then we have this one, that is eta minus 1, and then this one, that is xi plus 1. Now n2 at the rate 2 equals to 1. Therefore And similarly, you can obtain your equations for n3 and n4. If you open this, what you'll get is you'll get a constant term that is in the form a0 and then a1 xi. You get xi term, you'll get a eta term and then a xi eta term. Now here, if you look into the triangle, you can see that up to here your safe function equation is complete, but in that case we get xi eta as an extra term. Now let's look into a triangular element. Generally in triangle, what we do is we assume center point here for our coordinate axis, and this will be our xi and this will be our eta. Let's say this is node 1, this will be node 2. Now here, since this is 0, this will be 1 comma 0, as your minus 1 will be somewhere here. And similarly for eta, let's try to form the safe function for node 1. If we draw this in the isometric form, the line joining 1, 2 is xi, and the line joining 1, 3 will be eta. Now if you draw the safe function for 1, what you'll get is you'll have value 1 here, and then it will be 0 and 0 here. This is the xi direction, this is the eta direction. In both the direction you can see that this is linear. The value of the shape function in this line must be 0, isn't it? So your n1 must be 0 along this line. Now this line here, which is 2, 3, you have to find the equation for that line to cater for your point 2 and 3. Now the easy way to find the equation is to use the slope intercept form. So your equation will be given by xi by a plus eta by b equals to 1. Now these are your intercepts, so therefore it will be xi by, here it is 1, plus eta, here it is 1, equals to 1. Therefore the equation becomes xi plus eta minus 1 equals to 0. Now this is the equation for this line here. Now when you form equation for n1, so your n1 will be equal to c1 times, you can write this equation here, plus eta minus 1, and you see that you don't have any extra points or further points to consider because this equation caters for your points 2 and 3. Therefore this is complete. Your value of safe function at 1 must be equals to 1. Your coordinates at 1 is 0 comma 0, so you can plug these values here. Then what you get is, now when you plug this back in here, what you get is your n1 will be equal to, therefore this is your safe function for n1. Now let's look at node 2. Now when you plot your node 2, we have to find the equation of the line which contains these 2 points, because these are the only 2 points we are considering here, 1 and 3. Now the equation of the line that connects 1 and 3 is xi equals to 0. Therefore your n2 will become c2 xi minus 0, and this xi will contain nodes 1 and 3, and according to the definition, n2 equals to 1 at node 2. Now for node 2, your value of xi is 1, so it will be 1 minus 0. Therefore your c2 will be equals to 1. Therefore your n2 will be equal to xi. Now when you plot n3, I'll plot it here in different color. It will be 1 here, and it should be 0 here and 0 here. That means you have to find the equation of the line which contains these 2 points, and this equation of line containing these 2 is eta equals to 0. Therefore your equation n3 will be equal to C3 eta minus 0 at 3. Now these are your shape functions. Now you can add these up and see if the shape functions are correct, which means that your xi and eta cancel out and you'll have 1 remaining. So what to do now is we are going to move into higher degrees of shape functions. For this, let's try another triangular element. Let this be node 1, this is node 2, node 3, and then we add 3 nodes right at the midpoints here. So this will be node 4, 5 and 6. Now let's try to find the shape function for each of the nodes. Now here you can see that since we have 3 points here, this will be a quadratic shape function. So if you want to choose the polynomial of the shape function, then we have to go to the Pascal's triangle and then go to the quadratic equation. So you have to take all these points under consideration to look similar to this one. There you'll have xi square term, eta square term as well. Now let's try to find the shape function for 1. So if I draw this isometrically, now if you draw the shape function for 1, according to the properties, this should be 1 here, it should be 0 here and 0 here, and in the eta direction as well, it should be 1 there and then 0 here and 0 here, and at point n5 should also be 0. Now if we have this equation right here, then this one will include 5 in itself. Now this equation we had already obtained earlier. This will be, this equation here will consist of your nodes 2, 5 and 3. Now here we have to find another equation that contains the nodes 4 and 6. You can see here that if I make a line like this, then this line here will account for 4 and 6. Now the equation for this line is parallel to this one, so this will have a similar equation to this one. Now this line here will have equation of xi plus eta minus 1 by 2 equals to 0. Now you can see that we can form equation for n1 as n1 will be equal to c1 times, you see that this is quadratic, so it should have 2 linear equations. We can include this equation here, which is this one, and then we have another equation which is this one. Now this equation here will take care of points 3, 5 and 2, and this one will take care of 6 and 4. Therefore your n1 will be 0 at all these points, and it should be 1 at node 1. Then 1 will be equals to c1. Then what is your coordinate for 1? That's 0, 0. So it will be 0 plus 0 minus 1, 0 plus 0 minus 1 by 2. This will be equal to c1 by 2. Therefore your c1 will be equals to 2. And when you substitute it back here, then you'll have, following the similar procedure, you can get your n2 and n3 as well. Let's try to find what is n4. Now for n4, when you draw it, it should be 1 here, and it should be 0 along this direction, this is I, and along eta as well. Here you can see that the value of your shape function should be 0 along this line and along this line. Now this line here is xi plus eta minus 1 equals to 0, and equation for this line is xi equals to 0. Now you can form your equation directly, like, and here n4 equals to 1 at node 4. Your coordinates for 4 is half comma 0. So you write here half plus 0 minus 1 and then half minus 0. Therefore your C4 will be equals to minus 1 by 4. And therefore n4 will be equals to minus 1 by 4 xi plus eta minus 1. And similarly you can form n5 and n6 as well. Let's try. Now here, this equation, the line will be xi plus eta minus 1 equals to 0. And this line is xi equals to 0. And this line is eta equals to 0. Now if you write the coordinates of these points, then this one will be at 1/3, 0. This will be at 2/3, 0. And this will be 2/3, 1/3. This one will be 1/3, 2/3. This will be 1/3, 1/3. This will be 0, 1/3 and 0, 2/3. Now let's try to form n1. We're going to plot this in isometric form. Now if you plot your n1, it should be 1 here, and then it should be 0 at these points, at these nodes. You can see here that now is kind of like cubic curve, and here also it will be like this, and here it should be 0. Therefore you have to find certain equations which will connect these points. So this will be a cubic curve, which means that we are looking at up to here. So it will have xi cube, xi square eta, and eta cube terms. So when you go down, n1 will be equal to this line here. So you can write it down. This one will be c1 and then xi plus eta minus 1. And then you have to find another line which will include this one, these 3 points, or these 3 nodes. So this line will be parallel to this one. So it will be xi plus eta minus 2/3 equals to 0. So we have to include one more term here, minus 2 by 3. And then we have another one right here which connects 9 and 4. This is also parallel to this one. So it will be xi plus eta minus 1 by 3 equals to 0. And then we have to add one more here. This will be xi plus eta minus 1 by 3 equals to 0. Now at n1 at the rate 1 should be equals to 1. So n1 equals to c1. Now for 1 it is 0, 0. So it will be 0 plus 0 minus 1, 0 plus 0 minus 2 by 3, and 0 plus 0, and then minus 1 by 3. Now what do you get? Minus 1, minus 2 by 3, minus 1 by 3. Therefore c1 will be equal to minus 9 by 2. And then you can substitute this one back here and you can get your n1. And similarly you can get your n2 and n3. Now let's try to find n8 here. So for n8, what will happen is that at this point it should be equals to 1. It will be something like this, and then it will be 0 here, 0 here. And you can see here that your value here should be 0 along this line, 0 along this line, and 0 along this line here. So you have to find the equations of these 3 lines, and then you can form your equation. Now the equation of line joining 2 and 3 is xi plus eta minus 1 equals to 0. Now equation of this line here 1, 2 is eta equals to 0, and this one, since this is parallel to this one, This must be also in the form of eta equals to, now let's see what's the value of 9. That's 1 by 3. So this will be equals to 1 by 3. Therefore n8 will be equal to c8, and then you can write here xi plus eta minus 1, and then eta minus 1 by 3, and then eta minus 0, and then you can put xi equals to, what's the value of xi for 8? That's 0 and 2 by 3. So xi equals to 0, and eta equals to 2 by 3, and then say n8 at the rate this value here, that is the 0.8, should be equals to 1, and then you can substitute the values and obtain your c8 and substitute it back here to obtain your n8. And similarly you can find your safe function for 10 as well. So n10, it should be 0 along all these lines. All these lines contain all the nodes except 10. So you can directly form the equation for n9, that's equals to c9 times of this equation is xi plus eta minus 1. This is eta equals to 0. This is xi equals to 0. Therefore it will be xi minus 0, eta minus 0, and then xi plus eta minus 1. And here we can plug in xi equals to 1 by 3 and eta equals to 1 by 3 to obtain your c9, and then substitute it back here. Sorry, this is in c9, this is for 10. Now you see here, this is how we obtain our safe functions for triangular elements. Now let's move into rectangular elements again. Now for this case, what we generally do is we assume this one to be our xi axis, this one to be our eta axis. Now based on this one, this is the origin. We can label all our nodes. You can put the values of their coordinates in the natural coordinate system. If you plot safe function for this one, it will look something like this in the xi direction and something like this in the eta direction. So this will be kind of like a quadratic. We always look in the xi and the eta direction. Now you can see here that into the xi direction, which is this direction, you see here that it is 0 along this line and along this line as well. So this is in the xi direction. Now if you look into the eta direction, you will see that that line is 0 along this line and along this line. So this is in the eta direction. Now if you write the equations of all of these lines, then what you find is this line here has equation xi equals to 1. This one has equation xi equals to 0, and this line has equation eta equals to 0, and this line has equation eta equals to 1. Now you can combine all of these equations to form your shape function. So n1 will look something like this: c1 times you have your xi minus 0, and then xi minus 1, and then eta minus 1, and then eta minus 0. So this is your n1, and n1 at the rate 1, that is xi equals to minus 1, eta equals to minus 1. And when you substitute this one, what we'll get is c1 equals to 1 by 4, and then you can substitute this 1 by 4 here, and you can get your shape function for n1. Now let's try to find shape function for n5. So we're trying to find 5 here. So for this one, if I draw shape function for this one, it's going to look something like this in the xi direction, and in the eta direction it will look something like this, because this is 0 at 9 and 0 at 7 as well. So for this case, you see here that in the eta direction, n5 is 0 in this line here, and in the z direction it is 0 along this line and along this line. So the equation of this line here connecting 2 and 3 is z equals to 1. This is z equals to minus 1. This is eta equals to 0. 3 and 4 is eta equals to 1. Now you can form your n5 as c5. You'll have xi minus 1, xi plus 1, and then eta minus 0 and eta minus 1. So this will be of form c5. You can take this one like 1 minus xi square, and then eta minus 1, and then you have to solve for your c5 by putting your xi and eta as c5. Therefore c5 equals to 1 by 2, and then you can substitute your c5 here. Therefore your n5 will be equal to 1 by 2, 1 minus xi square, eta, and then eta minus 1. So this is your n5. Let's try to find n9 here. So for n9, you can see here that, let's draw it here, it should be 0 along this line, this line, this line, and this line. So along the boundaries it must be 0. So you can directly write n9 equals to c9. Then you'll have this equation here, xi minus 1, xi plus 1, eta minus 1, and eta plus 1. So n9 will be of the form c9 xi squared minus 1 and then eta squared minus 1. You can find the value of c9 by substituting here 0 and 0. Now you can see here that when you do that, c9 equals to 1. Therefore the equation for n9 will be, and this is how you obtain the values of your shape functions for 9-noded rectangular element. Similarly, you can have rectangular element like this. So this is a 22-noded rectangular element. Now for this case, your elemental matrix will be of 22 by 22. Now when you combine these elements in a structure, then you can get a very large stiffness matrix, which may be million to million. Now the idea here is to reduce the size of the stiffness matrix so we can increase our speed and efficiently use the computational memory. So when you look above, the way we found the shape function for n9, the 9th node, you can see here that this 9th node, which is inside the element, it has no contribution to element boundaries. So if we can avoid such kind of internal nodes, then what will happen is that in this case, if we can avoid these 6 nodes, then your stiffness matrix will decrease from 22 by 22 to only 16 by 16. This will dramatically reduce the size of your stiffness matrix, and then to also increase our computational speed. We can avoid this by assuming elements like this having only the boundary nodes. It will have no internal nodes. Such elements are known as serendip elements or serendipity elements. Now for this case also we can obtain our shape functions. Let's try to solve. Let's draw the shape function for the first node. Now what we'll have here is you'll get 1 here, and then it will become 0 like this, 0 like this. But you see at the central node you don't have 0 here. Now you can see here that our shape function must be 0 along this line. You have this line and you have this line as well. So to find equations of this line, and this line here, this is eta equals to 1, this line is xi equals to 1. Now this line is xi plus eta and then plus 1 equals to 0. This is the equation here. So you can write your equation n1 as, and here you can substitute your xi and eta for 1. There is minus 1 here, minus 1 here, minus 1 and minus 1 here, and you can solve for your c1. Now your c1, if you solve like this, should be equal to, so this is your shape function for n1. Let's try to find shape function for n5. So if you draw, so n5, what you'll have is you'll get this one as 1, so it will be 0 along this line, and this line. So we have to use 3 equations for this one. So what you get is this one, and this one. So what you can write here is for n5 equals to c5, this equation here, 1 and 4, this one is xi equals to minus 1, so this is xi plus 1, and then 4 3, this is eta minus 1, and then 2 3, that is xi minus 1. So this is our n5, and you can substitute your c5 back here and you get your equation. So let's try. Now when you plot for 1, there should be 1 here, it should be 0 along these lines as well, like this. So here also must be 0 0 and 0. So you can see here that your shape function must be 0 along this line, and this line in the eta direction. So this is eta equals to 1/3 for this one, and eta equals to minus 1/3. This equation for eta, and in the xi direction, what you can see here that it is 0 along this line, and along this line. So this is xi equals to 1, this xi equals to 1/3, this is xi equals to minus 1/3. So you can combine all this and say, okay, n1 equals to, and similarly let's try to find n5 here. So n5, I'll draw it in different color. So let's see, let's draw our n5. So our n5 will be 1 here, and then it should be 0 here, 0 here, and then 0 here, and in the other direction it is linear like this. So for this case you can see here that it must be 0 along this line, along this line and along this line. So for this one, what you have to do is n5 will be c5, you can write here. So for this one it should be 0 along xi minus 1, so right here xi minus 1, and then other one is xi minus 1 by 3. There's this line and this line, and then we have the other line, that is this one, that is xi equals to minus 1, so I'll have xi plus 1 as well. And in terms of eta direction, what we'll have is we have, and then we don't have any other xi's here. When you draw this in the isometric form, this will be 1, and then like this in the xi direction, and like this in the eta direction. So in this direction you don't have any other, no other points, because all the points are already considered by these equations here. Let's try to do n6 as well. So n6 will be equal to c6. Now for n6 it is something like this and linear here. So what you can write here is c6 xi plus 1, and then xi plus 1 by 3, and then xi minus 1, and then we have eta minus 1. That's it. Let's try to write it for n8. So n8 will be equal to c8. Now for this one, to be 1 here, and then become 0 0, and then 0, and then it will be linear in this direction. So this is our xi, this is our eta direction. So in the eta direction you can see here that it is 0 along this line, it is 0 along this line, it is 0 along this line. Therefore you can write n8 as eta minus 1, eta plus 1 by 3, eta plus 1, and then xi plus 1. That's your n8. So this is how you can obtain your shape functions for 2D elements. Now there's another way to solving the shape functions by using the Lagrangian polynomials. So we'll discuss briefly on the Lagrangian polynomials now. It states that if you have certain points, let's say x0 comma y0, x1 comma y1, x2 comma y2, and so on to xn comma yn. So these are the data points. So when you plot this, what you'll get is you have your x, you'll have your y, and you'll have these different sets of points like this. Now if you want a curve that can approximate these values with a polynomial like this, then this polynomial, let's define this as fn of x, where n is the order of the polynomial. Then your fnx, this interpolation function, is given by summation of certain weight functions times of their functional values. Now these functional values are y0, y1, y2 to yn, and this is called the weightage factor. So you can write this as your function fn x. Now this one actually goes from I equals to 0 to I equals to n. Now here fnx will be equal to summation I equals to 0 to I equals to n Li x times y I. If we expand this, we can write, I can see here that this is similar in writing our solution, our displacement solution, which is ux in the form n1 u1 plus n2 u2 plus n3 u3 and so on. And then here these ones were the shape functions. If we compare these, you can see here that this here L0, L1, L2 and Ln will also be the shape functions, given that these ones are your nodal displacements. Therefore, what we are interested here is only in obtaining the Lix, which is the shape function. Now Lix here is given by multiplication of k equals to 0 to k equals to n, where k is not equals to I. This is x minus xk divided by xi minus xk. Let's expand this function and see what we get. This is just a multiplication of these terms. So if you expand it, what you'll get is you'll get x minus x naught by xi minus x naught, and then x minus x1 divided by xi minus x1 times x minus x2 divided by xi minus x2, and so on. And then your k, this one, cannot be equals to I. If that is equals to I, then you don't have a solution here, you get infinity. So therefore, after this, what you'll get is x minus I minus 1 divided by xi minus xi minus 1, and then you won't have your xi value. What you'll get here is x minus xi plus 1 divided by xi minus xi plus 1, and then we go to the end, x minus xn divided by xi minus xn. So this will be your expanded form. Now let's try using this to obtain shape function of a bar element. What we have for a bar element is, right, so this one is of x1 y1, this one will be x2 y2. We'll use our Lix equals to product. You can start from k equals to 1 here, because we have x1 y1 rather than x0 y0. So what we'll do here is we'll write k equals to 1 to k equals to n, and then k not equals to I, and here we have x minus xi by xi minus xk. Now let's open this. For this case, we know that it's going to be linear, so therefore this one will be equals to 2, where you have the number of terms here. So that one will be equals to 2, starting from 1 to 2. So your L1x, that's the shape function for this node here, this is 1, this is 2, will be equal to product of k equals to 1 to n equals to 2, where k not equals to 1, and then we have x minus xi, xi minus xk. Let's expand this. What you get is x minus, this one must be xk, so this one will be, first k will be equals to 1, but in this case k cannot be equals to 1, so we go to k equals to 2. So this will be k x minus x2 divided xi. Your xi is I equals to 1 here, so x1 minus x2. So you know that x2 minus x1 is L, so x minus x2 by L. So that's your safe function for L1. For L2, so L2x would be equal to n equals to 2 product k equals to 1. K cannot be equals to 2 here, therefore x minus xk and then xi minus xk. So your k cannot be equals to 2, so k will only be equals to 1 here. So this one x2 minus x1. Yeah, this one should be equals to minus, because x2 minus x1 is L, so this should be equals to minus. So this will be equal to x minus x1 divided by L. So this is our safe function for N2. You can check these safe functions for the bar element as well. So let's try this in obtaining safe function for a bar element having 3 nodes. So in this case, when you plot your safe function for n1 as per the definition, this should be equals to 1, and then this should be equal to 0 here, and then this should also be equal to 0 here. Now if you plot for n2, so this is our n1. Now for n2, if I use a different color for n2, your n2 must be 1 here, and then it should be 0 at 2 and 3. Now this is n2. Now for n3, this one must be equals to 1, and this one must be equals to 0, and this one must be equals to 0. So this is n3, orange one. So this is how your safe functions should differ. Now this one, the coordinate for this one will be x1 y1, x2 y2, and x3 y3. If you want to find equation for this, then what you can do is you can write n1 as a function of x will be equal to product of k equals to 1 to k equals to 3, and k cannot be equals to 1 here, and then x minus xk, and then xi, x1 minus xk here. Now when you expand this, what you'll get is this one cannot be equals to 1, so x minus x2 here, this will be equal to x1 minus x2 times of x minus x3 divided by x3 minus x1. So this is your shape function for n1. And again for n2, x, what you get is x minus x1 divided by x2 minus x1 times of x minus x3 divided by x3 minus x1. This one must be 1 minus x3. This one also should be x2 minus x3. And similarly, n3 as a function of x will be equal to x minus x2 divided by x3 minus x2, and then x minus x1 divided by x3 minus x1. So these are your shape functions in this case. Now you can do this for xi and eta as well. In this case, you can have xi axis here, and you can have 3 points, this one, and this one. You can have this one xi at -1, xi at 0, xi at 1, and this can be your node 1, node 2, node 3. Now in this case, you can look back here and you can substitute the values of the coordinates. Now let's see what you get. So you can have n1 as a function of xi will be equal to, so you can write it directly now, xi minus xi2 by xi1 minus xi2, and then we have xi minus xi3 divided by xi1 minus xi3. Now when you plug in the values of xi2 and xi3, you can see that you will have xi minus, now your xi2, that's for the second node, is 0. So we'll have 0 here, xi1 is -1, and xi2 is 0. So we'll have 0 here. And for this case, we'll have xi minus xi3. Xi3 is 1, this one. And then we have xi1 minus xi3. Now your xi1 is -1 and then -1. So when you look at this one, what you get is xi minus 1 divided by -2 and then that's 2. So we get half xi into xi minus 1. If you look at n2 again, so n2 xi, this will be equal to, so this is n2. And similarly you can find n3 as well. So this is how you can obtain your shape functions using the Lagrangian method. Let's try to find a shape function for a 4-noded rectangular element using the Lagrangian polynomials. Now for this one, let's try to find this here. Now you see when you plot this, you get a linear shape like this and linear in this direction as well. So it must be 1 here and 0 in this direction. Now here in the xi direction, so we have to look in 2 directions for this case because this is 2D. So in xi direction we have point 1 and point 2. This is kind of like a bar element. This is linear with node 1 and 2. So for the xi direction, your equation L, so this is linear 1 for 1 in form of xi will be equals to, you can write here directly that xi minus xi2 by xi1 minus xi2. So this will be equal to xi minus what's xi2? Xi2 is 1 and then xi1 is -1 and then we have -1. So this equals 1 by 2 xi minus 1. And for L1 in eta direction, you can see here that it is linear in this direction as well. So this will be equals to eta minus eta 4 divided by eta 1 minus eta 4. So eta minus what's eta 4 here? Eta 4 here is 1. 1 divided by eta 1. Eta 1 is -1 and then here this is 1. So this will be equal to -1 by 2 eta minus 1. Now here in the Lagrangian one, you have to find the product of L1 xi and L1 eta to get your total shape function. So L1 as a function of xi eta will be equal to L1 xi times of L1 eta. So this will be equal to, so if you want to find n2, it will be linear in this direction, it will be linear in this direction. Therefore for L2 it will be similar. So L2 you can write here xi eta directly. You can see that in xi direction, which is this direction here, it will be xi minus xi1 divided by xi2 minus xi1 times of eta minus, you have eta 3 in that direction and eta 2 minus eta 3. Now you can plug in the values and can get your L2 as well. So this is your shape function for second node. This is the shape function for the node number 1. Let's say you have 9-noded rectangular element as well, and you want to find your shape functions using the Lagrangian method. Now for this case, you want to find your shape function for n1. Now you see here that your n1 will vary quadratically like this in the xi direction and quadratically in here like this, maybe something like this. You can write your n1 as a function of xi and eta as, so you can write here xi minus xi5 in this direction by xi1 minus xi5, and then you can take this one as well. So it will be xi minus xi2 divided by xi1 minus xi2, and in the eta direction we can write eta minus eta 8 divided by eta 1 minus eta 8 times of, you have eta minus eta 4 divided by eta 1 minus eta 4. Now you can plug in the values here. So what you get here is xi minus xi 5. Xi 5 is 0, which is this value here. Xi 1 is minus 1, and then again xi 5 is 0, and then you have here, this is xi minus xi 2. Xi 2 is 1, and then xi 1 minus xi 2, so minus 1 minus 1, and then here eta minus eta 8. Eta 8 is 0, so you have eta minus 0, but eta 1 is minus 1 minus 0, and here we get eta minus, that's 1, and here minus 1, and then minus 1. Now what you can write here is, so this is xi minus 1, eta minus 1, and then here minus 1 times minus 2 times minus 1 times minus 2, that's 4. So 1 by 4 we get xi minus 1, and then eta minus 1. So if you want to find n5, you have to take in account n1, 2, 9 and 7. So you can form two equations in xi direction and in eta direction and then multiply them together. So similarly you can find your n5 as well. So if you want to find n9, you have to take into account n8, 6 and then 7 and 5. Let's try n9. So here if I write n9, this will be equals to xi minus n9. So I can write 6 and 8 fall in xi, so I'll write xi 6 divided by xi 9 minus xi 6, and then xi minus xi 8 divided by xi 9 minus xi 8, and then here eta, I'll have eta in 7 and eta in 5, so eta minus eta 5 divided by eta 9 minus eta 5, and then eta minus eta 7, and then I'll have eta 9 minus eta 7. Let's put the values in. So we get xi minus, what is xi 6? Xi 6 is 1, and then what is xi 9 is 0, so 0 minus 1, and then this will be xi minus, what is eta 8? Eta 8 is, what is xi 8? Xi 8 is minus 1, so plus 1, and then we'll have 0 plus 1 here, and then for eta we get eta minus, what's eta 5? So eta 5 is this one, that's minus 1, so this will be plus 1 and then 0 plus 1, and then eta, what is n7? 7 is 1, so eta minus 1, eta minus 1 divided by 0 minus 1. Now when you look at this, what you get here is 1, 1, and then 1, that's 1, so you get xi square minus 1 and eta square minus 1. So this is how you can solve for your safe functions using the Lagrangian method as well. So this is all about obtaining safe functions using different methodologies. You can either use Lagrangian method, or you can use the normal geometrical method that we did before. So this is it for today. Today we learned about safe functions and the ways to obtain them in a 2D triangular and rectangular elements having different number of nodes. You can have internal nodes and nodes at the boundary elements as well. And we also looked into the Lagrangian polynomials, where you can obtain your safe functions by using its weightage factor. Thank you very much for watching till the end. I'll see you next time. Cheers.